Just had to open a couple things up. I don't really need that. Because in the relations and functions stuff, the outcomes kind of fly fast and furious. We've done transformations, which we had done with the trig stuff. We looked at reflections and stretches and all that sort of stuff. Then we did inverses, which, oh, let's share screen. So inverses were fundamentally reflecting something in y equals x. For a linear function, it's not such a big deal. What is it? No, that's not down there. For a quadratic function, we get something like the red graph, and we talked about how technically the inverse of y equals x squared is not a function because it doesn't pass. I don't know what just happened. The vertical line test. So because a function is defined as something that has, for every x value, there is one and only one y value. And well, for x equals 4, this has 2. So the next section that I put up, the beginnings to, is radical functions, which we can look at these in terms of all sorts of different things. We're going to start with just, why does that keep popping up? Y equals the square root of x. And we're going to do the things that we did kind of with. Everything okay? Technically with sine, we'll do that again with exponential functions and logarithmic functions and the like. So that's where we go. Because if we start at y equals x, or the square root of x, y equals negative the square root of x is just a reflection in the x-axis. So if we go way over to here, we're looking at y equals the square root of x. It's the base radical function, just like when we did a parabola, y equals x squared. I can't remember whose is whose. I think that's his. Sorry. When we did transformations of sine and cosine, technically y equals sine of theta or x. These are our base functions. Oh, the other one that you did in pre-calc 11 is the absolute value of x. I assume and hope everyone can hear me. My wife had a meeting and it's like, well, I'm going to stay upstairs and just in case kids go crazy and all of that. So we're starting with a new function. We're going to look at mapping rules and equations and all the stuff that we've done with anything. We did it originally with transformations. Y equals f of x and y equals a f of 1 over b x minus h plus k. That's what we did the other. Now instead of f, we're going to have a 1 over b x minus h plus k. And we need to be able to figure out what the transformations are. We need to be able to develop a mapping rule. We need to be able to do all of the things that we've done with just dummy things with this square root of x. So if I have y equals 3 times the square root of x minus 4, we have an a value, so we have a vertical stretch of 3. There's nothing under the radical, so we have a vertical translation of minus 3. So the next slide we'll talk about graphing them in the base graph, but just familiarizing ourselves with these sorts of things, then we can go through and build everything. Well, I've got a 2, that's a B's. This one has a horizontal stretch of a half. We have an H, so this has a horizontal translation with the opposite sign of -5. So whatever the graph of this is going to be shrunk down and moved. Oh, to me it's moved to my left. I guess it's moved to everybody's left, but how I'm looking on camera might be a little different. So if we have a base function of y equals the square root of x, and we have, here are our transformations. Vertical stretch is a, our b is 3, our k, and our h. Can we put that into this equation? Well, yes, I would hope so. Y equals 4 times a great big square root of 1 over 3 x minus 7. Let's just shorten that a little bit. Plus 6. And with these, we're going to kind of look at a point like the vertex. If this was a square, the vertex would be 7, and, or if it was a quadratic, the vertex, and we're going to have a point similar to that. Now can we make a mapping rule? Because the easiest way to do these is with a mapping rule. I'm going to list my transformations. Well, this has a horizontal stretch of a half, horizontal translation of 6. So our mapping rule, like, this is why in hindsight, if I had have done this whole course, I would have started with transformations, because when we do graphing trig stuff, everything would be so much simpler. A half x plus 6. Y doesn't change because there's nothing there. Can we write an equation based on a mapping rule? Well, yeah, this has a horizontal translation of -4, a vertical stretch of 3, a reflection in x, and it has a vertical translation of +2. Y equals negative, because that's the x reflection, the vertical stretch is 3, square root of x plus 4, plus 2. So far so good. This, like, hopefully this is all stuff we can kind of remember, at least looking at, seeing with the other things. It's also why this kind of method makes like, we want to know the base graph. If we can, based on this, and put it in this kind of, well, it used to be called transformational form, figure out what a new graph looks like. It's all about trying to do this stuff with our brains. Horizontal stretch of a half, reflection in y, and then it's got a vertical translation of -3. Y equals nothing. A horizontal stretch of a half means I do 2. Oh, -2 x, because there's nothing else. Make that a little shorter. -3. So this one's going to be shrunk and shifted up. Can I do a mapping rule straight from this? The x business goes first. So negative x plus 2, the y part, 3y plus 5. So that is our kind of review connection of transformations. Now can we look at what the graph of the base function looks like? Can we use that information given an equation? Can we find our key points with sine, well, let's go to a parabola. We hit the vertex, and then we have a pattern with a sine or cosine. We had middle, high, middle, low, middle, and if you transform those 5 points to wherever you want to go, you get a new graph. With an absolute value function, it would be similar. And now with one of these, if we get our base graph, we look at some key points. Can we take an equation? Can we write a mapping rule? Can we take the mapping rule and sketch the new graph? Because when it comes to calculus and other things, it's not necessarily always about knowing exactly where all of the points are. It's knowing about what shape of the graph and where it is. So our base function is y equals the square root of x. So we could do this in the sense of an inverse, but if I'm trying to build a table of values, if we did a parabola, we would start at, if you had me for foundations, you started at -3, -2, -1, da 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 da. Because my math teacher in grade 9, when we built thousands, well not thousands, hundreds of tables of value, that's what we started with. And that's fine for a parabola. It's fine for an absolute value. It's fine, well, not really fine for a sine or cosine. But for a radical, does starting a table of values make sense here? This is where hopefully someone unmutes and says, can we take the square root of any of these? None of those are defined. We can't take the square root of a negative number, so all of that stuff is irrelevant. We don't care. So let's start our table of values at 0. If y equals the square root of x, what's the square root of 0? Well, that's easy. 0. Now this is where we're going to be selective. When we did trig, our initial graph was 0, pi over 6, pi over 4, pi over 3, pi over 2, and we did that whole giant thing. Well, just quickly, 1. Okay, that's the next one. What's the square root of 1? Well, that's easy. 1. Okay, cool. 2. Oh dear. The square root of 2. Can we plot that? That's approximately 1.41, yada, yada, yada. I'm not going to try to plot it because it's ugly. I'm going to extend this a little bit. The square root of 3. Well, that's the square root of 3. I think it's 1.73, give or take. Okay. Awesome. I don't want to plot that because both of those are irrational. They're hard to plot. Oh, 4. What's the square root of 4? Well, I know that is 2. 1, 2, 3, 4. Up 2. 5, 6, 7, 8. Those are all kind of ugly. 9. 1, 4, 9. Those should be familiar from a parabola because this is the inverse of that. The square root of 9 is 3. I could keep going, but I don't have space. If I had been smarter, 16 is 4. So it's going to keep going up. 25 is 5. But the general shape of this graph,
Brody, I just got removed from the meeting.
from what?
I just got removed from the meeting.
But you're right there.
Yeah, I just got removed. I joined back.
Oh, are you able to kick? I know I can kick
Well,
you out.
Brody kicked me out of the physics call the other day. So that's the first person I assumed who it was. But
No, it wasn't me. I
well, I
couldn't.
didn't say it was you.
Oh no. It probably was Brody. I don't know. There's some other people who are there that might do that.
Yeah, that was me. I'm sorry, Brady.
Yeah, that's what I thought.
So we have our wonderful graph. We can look at a domain. The domain of this is the x values. Can we have a value of x that's less than 0? In this case, x has to be greater than 0. X is part of the reals. The range, this is a little bit different. Well, that's our smallest value, 0, 0 for the base function. Y can't be less than 0 as well for the square root of x, and that will continue on. It's always going to keep getting bigger because 25 is 5, 36 is 6, 49 is 7. It's going to keep growing. It's not going to grow at a very large pace. So really, when we're doing one of these, we have 1, 2, 3, kind of maybe 4 points, depending on where the graph is going. So trig, we had 0, 90, 180, or whatever, and we knew those ones. It's the exact same idea. It's just we're really going to be looking for that point, which is similar to the vertex. Over 1 up 1, over 1 up 1, 2, 1, 2. Oh, whoops, sorry. Let's fix this because I can't count. 1, 2, 3, 4, and up 2, 9, and up 3. Dang nabbit. I had an actual nice graph. Sorry. Someone should have said, hey, McKay, you can't count. So that's our base graph. So what we're going to do is, in this kind of outcome, well, we're going to plot 3 of them by, I really like the basement better, mapping rule. Figure out the mapping rule, key points. Eventually, if you had time to practice all sorts of stuff, you'd be able to look at that graph and say, okay, it's not technically a vertex, but I know where the initial point is for this one. It's not stretched. I can do everything. I know where all of the different things are. So these get to be, or should get to be, or could get to be similar to what a lot of you have with parabolas and quadratics. It's like, okay, if it's in this equation, I can draw this graph without even thinking. And that's ideally where we want to go. So this one has a mapping rule. It's got a horizontal translation. This is going to switch to x minus 4. Don't close the bracket yet, silly. And a vertical translation of plus 5. So our kind of key points were 0, 0, 1, 1, 4, 2. This one, just because I know 9 and 3 is going to work, x minus 4 is negative 4. Y plus 5 is 5. 1, 2, 3, 4. 1, 2, 3, 4. 5. 1 minus 4 is negative 3. 1 plus 5 is 6. 4 minus 4, hey, that's 0. And 7. 0, that's 6. And 1 is 7. And if we were doing this in class, there, that's all we would do. But because this one kind of, I know that that's going to be translated for, well, to my left. I think I'm pointing to your right. 9 minus 4 is 5. 3 and 5 are 8. 1, 2, 3, 4, 5. And right there, there's the graph of y equals the square root of x plus 4 plus 5. So far, so good. Fairly straightforward, I hope. So I think if you've looked at the file, I added this one after because I wanted to have that in there as well. So a mapping rule for the next one. There's nothing with the x. The y is negative 2y minus 4, 0, 0, 1, 1, 4, and 2. 0, x goes to x. So technically, all of these are going to be 0, 1, and 4. And then we get to see where our y coordinates are. Negative 2 times 0 is 0. 0 minus 4 is negative 4. Negative 2 times negative 1 is negative. Negative 2 times 1 is negative 2. Negative 2 minus 4 is negative 6. Negative 2 times 2 is negative 4. This is negative 8. So 0, 1, 2, 3, 4. 1 and negative 6. 4, 1, 2, 3, 4, and negative 8. Wow, that was awful. Oh my lord, this is such a pain in the butt. 9 would be something. So notice this one has a vertical stretch of 2. Our initial graph, just like the parabola, goes over 1 and up 1. This one goes down 2. I guess I wanted that vertical part. So we can stretch that up. Instead of going up 1, we now stretch it by 2. But this is reflected, so it goes upside down. So we can do all of the transformations that we've done. Sorry, this chair is horrifically uncomfortable. Like so. One more, and then I will point you in the direction of the next file, which has some other things. So are we good so far? X, Y, just because I want goes to, well, I now have a horizontal stretch of 2. We have to be careful. This radical stops here, so that's just 2x, and the y is plus 1. And we can add all sorts of different things. No, where did my cursor go? What's going on? So 0, 0, 1, 1, 4, and 2. 2 times 0 is 0. 2 times, or 1, 0, 1, 0 plus 1 is 1. 2 times 1 is 2. 1 plus 1 is 2. 2 times 4 is 8. And 3. So now we have 0 and 1. That's 0 and 0. 0 and 1. 2 and 2. So that horizontal distance between the first 2 points is now 2, and then 8 and 3. So this one has gone up 1, but now it's elongated by a factor of 2. So same idea as what we've done before. Well, I'm just gonna, hopefully that's mine. So there are 2 pages here, and then we'll look at some other stuff tomorrow. State the transformations, write a mapping rule, stuff that should be fairly straightforward, write an equation. Well, that is a freebie. Use the base graph, do a mapping rule, draw a graph of this. Use the base table of values, write a mapping rule, draw a graph of that. Everything fairly similar to what we've done. After that, there's some other things that I have to kind of redo. We'll look at some domains and ranges, and then we'll look at square rooting of functions in general, which is a little bit different. What's the graph of the square root of 2x plus 2 equal? Well, that's a little bit different.
Mr. McKay.
Yes, sir.
Are you? I don't mean to be rude, but are you wrapping up? I've got to go put my car out of the shop.
Yeah. I'm more or less done.
Okay.
Aiden emailed me and said he was asked to work in the mornings and was like, I'm not ditching class. It's like, well, there's no class. I can't force any of you to do anything. So
Okay, sweet. Thank you.
no problem. See you later. So your quote unquote homework, and I'll go over this quickly tomorrow, is to look at that. Go away. Where was I going? And then we'll look at some graphs and then some what are called invariant points and how those go. The problem with what? Oh, okay. I opened that up, and when I hovered, it just had like a minute, and I was like, "What? Did I not record this? Oh my gosh!" Sorry. I had a little bit of moment of panic. So we'll look at a little bit more with this tomorrow. Tomorrow's Friday, then we won't be back together until Monday. Hopefully it's supposed to rain on Saturday. Not tests. This is for those of you who are interested. There have been some people reporting that they had COVID-19, recovered, and then tested positive again. And in Korea, where they do testing galore, they're not reinfections, which means all sorts of good things. So that's it for me today, unless anyone has any questions.
I do.
Okay.
So are you gonna, after we do like our little like homework, whatever you said that like those questions you gave us, are you gonna put like in a file like the corrections given?
For these ones? Or yeah, we'll go over them quickly tomorrow as well.
Okay.
Just like if things aren't clicking or whatever, because a lot of times a lot of people just seeing things that in class you see things more than once. A lot of the stuff I would go through, and there would be a little bit more back and forth, which if you want to answer questions, there's absolutely, you guys are really very polite and don't like to unmute. Can I unmute you? No, I can just mute people if I want to. Like if you have questions, speak up and say, hey, or if I make mistakes or things like that. But we'll go over that and talk about a little bit more tomorrow if that helps. I mean,
Okay. And so did you say will it be in the files or do we just wait till tomorrow for it?
well, I'm gonna go over it tomorrow So like I'll go through, because it shouldn't take too long to actually just do. I might skip like some of like that graph. I'm probably just going to skip and then focus on the rest of them, but that shouldn't take more than 10 minutes to go over tomorrow. So try it and we'll go over it. And if you have questions, you can ask.
Okay.
Sound good?
Thank you.
No problem.
Do you always use those same points?
Yep. It's
Like
just,
the 4, 2, 3, or 9, 3?
well, you would just in general start with the 0, the 1, and the 4, those three. It's the same idea as the high, middle, low, middle, high. It's that same kind of concept. You know those are the points. If you know what the shape is. For trig, we knew that it was that nice sinusoidal curve. So if I know those and I can move those, I can fit my stuff to those. For a radical, I know it's going to just kind of go up gradually. When we do exponential functions, it's going to be the same sort of idea. So a lot of graphing isn't about getting a whole bunch of points. It's about knowing what the key points are and manipulating them, if that helps. I think that's the answer or what you were asking.
Got it. Thank you.
Okay. All right. I will sign off and see you guys tomorrow. Have a good afternoon. Enjoy the sun.
Thank you.
You're welcome.